Hey, this is Tim Malloy with a far overdue video 1-3 electric potential. I chose problem 6, so here we go. Two insulating spheres have radii zero point 0.3 centimeters and zero point 0.5 centimeters, masses 0.35 kilograms and 0.7 kilograms, uniformly distributed charges of -2 nanocoulombs and 2.5 nanocoulombs. They are released from rest when their centers are separated by 1 meter. A asks how far will each be moving when they collide. Hint, conservation of energy. Oh, my pen isn't working. What? Okay, the pointer's not working. I'll just use the pencil instead. Okay, hint, conservation of energy and linear momentum. So first off, I drew a diagram. So here we have sphere 1, that's our mass, charge, radius. Again, sphere 2, mass, charge, radius. Interesting how the masses, one is double the other. That will be important later. Not really important. Like it's actually, not too crazy important, but it is something, a cool realization I had later that I will make sure to share. So again, part A is velocities or speeds rather than unit speeds, and they say hint use energy, so let's use energy. Hey, remember electric potential energy? It's different from electric potential, which is something that I had forgotten for a while. But anyways, I guess that's just some strange wording. So we start out, and these spheres are separated and not moving. So we just have electric potential energy. And then after they're released, we have kinetic energy. One sphere is moving, kinetic energy, second sphere is moving, and we still have electric potential energy. And that's because even when the spheres touch, I'll mess around with this. Even when the spheres touch, there's still a distance between the centers. They're still attracting one another even though they're touching. And again, I just put that here. So set up our equation and then take our types of energy and get their formulas. This is formula for electric potential, kinetic. We know kinetic very well, but again, the electric potential one right there, two charges over a radial distance from centers. This is initial, that's final. But these two, the charges and obviously the constant are the same. Okay, so we have all the values, except we don't have V1 and V2. So let's try to use momentum for that. So at the start, I drew my momentum bar graphs. So at the start, spheres aren't moving, no velocity, zero momentum. And then when they're done moving, or I guess at their point of collision, rather, we have the orange sphere, which I think is sphere 1 is lighter, so that's why it is less long on my bar graph, but it's moving faster, which is why it is wider. And then pink is vice versa. It is longer because more mass, shorter because more, or less wide because less speed. We get our equation from this, set it equal to V1, plug, this is just our original equation, and then we plug that original, what am I trying to say? We plug the V1 into here, and then at this part over here, I just put the values in. So KE, charge, that initial distance that we were given, and then masses. We don't have a V2, so we keep that as a variable. And then just another kinetic energy, another electric potential energy. Thank God for the solve function. Then we get V1 equals 4.61 meters per second, and V2 equals 2.3. Notice how one is 2 times the other. Again, I'll touch on that at the end. And then so that's part 1 done. We have both the speeds. Part B is saying if the spheres were conductors, Would the speeds be greater or less than those calculated in part A? And then a reference point, whatever, v equals 0 at r equals infinity. So my thinking on this was, we know conductors welcome charge. They're not like insulators where they won't really take it in. So these conductors would have a greater attractive force. Again, they like charge. They like to be charged, or they welcome it. I don't think they have feelings. I don't think they want anything in life, but that's just their natural properties. And so they have a greater attractive force, and they will have a greater speed because more acceleration. They're applying more of electric field acceleration on each other. So greater speed. And then here we go, just checking our answers. All good. So here are my takeaways. Wow, not that bad when you set up the energy equation. You find out that your momentum, the way that you work momentum into this problem is rather simple. And then since mass 2 was 2 times mass 1, then it would make sense that V1 is 2 times, or V1 is 2 times V2 because conservation of momentum. How cool is that? And then you can look at the bar graph again, makes sense again. This is 4 by 2, and then this right one is 4 by 2, and then this is 2 by 4. Watch the energy conservation with the electric energy at the end. Again, there's still distance between the centers when they collide. And then I congratulate myself for putting my diagrams on grids and including all of them. I deserve a 10 out of 10. Thank you very much. But that's it for the video. Thank you for watching.